Thank you for a warm welcome and invitation to IBS seminar. Today I will talk about Evencycle matroid. This class of matroid are interesting because these matroids are a generalization of graphic matroid, and they also have graphical representations. This is partial work of my thesis, and is joined to work with my advisor, Bertrand Guinan and Irene Pivotal. So let me start with the simplest class with graphical representations, which are graphic matroid. So for a graph in this talk, we allow parallel edges and loops, and the cycle of a graph is a simple closed walk of the graph. So this is a easy example. So this is an easy example, and a matroid M is graphic if there is a graph G such that circuits of M are precisely cycles of G. So we denote this by M equals to cycle of G. And when a class of matroids have graphical representations, two fundamental problems arise naturally. The first problem is called isomorphism problem. So we want to describe the relationship between two graphs that represent the same matroid. And the second problem is called bounding the number of representations. And we want to know how many graph representations a graphic matroid have. Before we talk about the answers of these problems, I want to talk about how can we get another representation from one given representation. So there are two operations called Oneflip and Twoflip. So Oneflip is basically we pick two vertices from different components and identify those two vertices, or the reverse operation. So basically, you can consider this operation as a rearrangement of blocks. So this operation preserves the set of cycles because every cycle is contained in the unique block of the graph. For Twoflip, this is more complicated. So first of all, we need to take two separation of a graph and separate the graph according to the boundary of the vertices, and flip one part upside down and identify those two vertices again. So these arrows indicate that we flip the right hand side upside down. And we say that two graphs are equivalent if we can obtain one graph from another graph by a sequence of one flips and two flips. So we denote this by this notation. And there's a very nice theorem proven by Whitney in 1933. So this theorem says that two graphs G1 and G2 represent the same graphic matroid if only if they are equivalent. So this gives the answer for the first problem, isomorphism problem, directly. And this also gives a partial answer for the second problem. So let me explain this. So consider this example. So this graph has many subgraphs, P1 to Pk, and they share two common vertices in the middle. And pick a subset of Pi's, and we apply two flips on every Pi in A. So those are two flips. So we can get another representation for the same graphic matrix. Because we pick A arbitrarily, so this implies that there can be exponentially many representations. Well, in the other word, by using the Witten's theorem, we can say that there is the unique equivalence class. And this gives the nice answer for the second problem, because Witten's theorem implies that for a graphic matrix, there is a unique equivalence class. So why do we want unique class instead of exponentially many representations? Because if we can bound the number of representations up to equivalence class with a constant number or polynomial number, we can use it to construct a recognition algorithm. So we want to construct an algorithm to recognize if a given matrix M is graphic or not. So this is not the topic of today's talk, so let me explain briefly. So for a given matrix M, we want to know whether this is graphic or not. So first of all, we construct a sequence M0, M1 to Mk such that M0 is the given matrix, and for each I, Mi plus 1 is 1h minor of Mi, and size of Mk is bounded by a certain constant. And here's the algorithm, sketch of the algorithm. First, because size of the Mk is very small, we can find every equivalence class of Mk. By the Witten's theorem, we know that there is none or unique equivalence class. And for each I, we check whether we can extend this equivalence class from Mi plus 1 to Mi. So polynomial bound matters here because if there are exponentially many equivalence classes, for example, for each I, we suppose that we can double the number of equivalence class. So we start with the one equivalence class for Mk, and then we have two equivalence classes, and then 4 and 8. Then this algorithm is not polynomial complexity. So if we can bound the number of representations by polynomial number, then we can use it to construct the algorithm. Now let me talk about Evencycle matrix. So as I said, this matrix have graphical representations called signed graph. A signed graph is a pair of G sigma, where G is a graph and sigma is a subset of edges, and we call this sigma sign. An easy way to consider this signed graph is considering that every edge has parity, and sigma is a set of odd edges. So then we can define the parity of each cycle C. So cycle C is even if only if it contains the odd number of odd edges, which means intersection of C and sigma is even. So C is odd cycle if C contains odd number of odd edges. Then we define Evencycle matrix. M is an Evencycle matrix if there exists a signed graph G sigma such that circuits of M are precisely one of these three constructions. So one is Evencycle, and 2 and 3 are union of two odd cycles where they have at most one common vertex. And we denote this by m equals to E cycle of G sigma. Now we can consider the analogous problems. So for isomorphism problems, we want to know the relationship between two signed graph, G1 sigma 1 and G2 sigma 2, that represent the same Evencycle matroid. And also we want to know the nice bound for the number of representations for a given, oh, this is typo, for a Evencycle matroid. Sorry about that. And I will talk about mostly about the number one problem. And if we spare some time, I will talk about the second problem as well. So here's the isomorphism problem. So we have two signed graphs such that they represent the same Evencycle matroid, and we want to know the relationship between these two signed graphs. So we will start with the easy case, where for case 1, we assume that G1 and G2 are equivalent, and then we assume that sigma 1 or sigma 2 is empty set. For case 3, we assume that the Evencycle matroid is graphic, and we consider the other operations. So for the case 1, we assume G1 and G2 are equivalent, and here is another operation called resign to generate another signed graph representation from 1. First, we take a, so here's the example. So red edges implies, denotes the sign sigma, and we take a cos C, and we change the parity of all edges in this cut. So our new sign is sigma, symmetric difference of sigma and C, and actually these two signed graphs represent the same Evencycle matroid because consider any cycle, and in a graph, every cycle and every cut has a even number of edges as an intersection. So if we resign this cut, then we change the parity of even number of edges in the cycle. So this operation preserves the set of even cycles, and we say that this new sign signature of G sigma, and there's a simple remark saying that if G1 sigma and G2 sigma 2 represent the same Evencycle matroid and G1 and G2 are equivalent, then sigma 2 is a signature of G1 sigma 1. So actually the converse is also true. I mean, if G1 and G2 are equivalent and G2 is a signature of G1 sigma 1, and then they represent the same Evencycle matroid. So we may assume that G1 and G2 are inequivalent. For this case, to understand this case, I want to introduce another class of matroid called Evencut matroid. This is very similar construction as Evencycle matroid, and this class also have graphical representations called graph. So in this case, graph is a pair of graph and a subset of vertices called terminal. And we say a cut delta V for a subset of vertex subset V of vertices is even or odd if it has even or odd number of terminal vertices. Then we say that M is an even matroid if there exists a graph such that circuits of M are precisely inclusion-wise minimally even cuts of GT. So here is the example of even cut. So this is a graph with a graph and the terminal set 1 to vertices 1 to 5 and 6, and cut consider a cut DEF, and this cut is an even cut because if you consider this cut, we have 2 terminal vertices on the left and 2 terminals on the right. So this is an even cut. And we denote this matroid by M equals to E cut of GT. So why we care about this class? Because of this nice theorem called pairing theorem, proven by Ginan, Pivotal, and Warlan in 2013. So assume that G1 and G2 are inequivalent graphs, and the following are equivalent. So 1, there are signs sigma 1 and sigma 2 of G1, G2, such that G1 sigma 1 and G2 sigma 2 represent the same even cycle matroid. And 2, there are terminals T1, T2 of G1 and G2 such that G1 T1 and G2 T2 represent the same even matroid. So this implies that isomorphism problem for even cycle matroid and isomorphism problem for even matroid are the same problem. Moreover, if this is true, if 1 and 2 holds, then sigma 1 and sigma 2 are unique up to resigning, and terminals are unique as well. And this theorem actually gave more information. So if we know sigma 1, we know the information for T2 and vice versa. In specific, if sigma 1 is empty set, then T2 terminal set T2 is also empty set, and vice versa. So we can consider this problem as a problem of graphs, 2 graphs, instead of 2 signed graphs or 2 graphs. Yes? One and two are equivalent. That is also true, but the uniqueness is not true. Yes. Actually, sigma 1 is given, then sigma 2 is also given up to resigning. We have no choice if they represent the same even cycle matrix. And same for the terminals. Oh, sorry?
For the terminal matrix, what does it mean to be an even cut? Do you need the same number of terminals on each side, or is it an even number of terminals on each side?
Even number for each side. Yes. Yes. No more question? Okay. You mean even cycle matrix and even cut matrix? No. You mean dual of even cut? No, but later I will talk about a subclass of even cycle matroid called pinch graphic matroid, and we can construct a similarly pinch graphic matroid, and these two are dual for each other. So assume that G1 and G2 are inequivalent, and for case 2 we assume sigma 1 or sigma 2 are empty. So by the pairing theorem, we can have T1 or T2 is also empty set. And in 1982, she proved in his thesis that if sigma 2 is empty set, then we have one of three structures. So I will not talk about details, but this is one example. We have 6 pieces of triangles, and we can arrange them into like this. And red edges means sigma 1, and here sigma 2 is empty set. And these 6 vertices on the rim cycle are terminal 2, so T2. And here for the left graph, T1 is empty set. So this is one construction. And this is also Porcio and Guinan proved the shorter proof in 2020. And for case 3, we assume that G1 and G2 are inequivalent, and each cycle of G1 sigma 1 is graphic. If the matrix is graphic, then we know there is a graph G3 such that cycle of G3 also is also the same matrix. And we can see that each cycle of G3 empty set is same as cycle matrix of G3. Let me explain why. So if the sign is empty set, then there is no odd cycle. Every cycle is even. And what is the circuit of this even cycle matrix? So circuits are either even cycle or union of 2 odd cycles sharing at most 1 vertex. But there is no odd cycles in this signed graph. So circuit of this even cycle matrix is precisely circuit of a cycle of G3. So these two are the same matrix. Then we can apply the Schlick theorem twice for G1 and G3, G1 and G3. So we say that in this case, G1, G2 are graphic siblings. And we can do the analogous operation for case, I say 3 prime. So I just change the even cycle to even cut. And we assume that this matrix, even cut matrix is cographic. And if it is cographic, there is a graph G3 such that cut matrix of G3. So cut matrix is a dual of cycle matrix. Is the same matrix as even cut of G1, G2 and G1, T1 and G2, T2. So again, we can apply the Schlick theorem twice. So in this case, we say that G1 and G2 are cographic siblings. For case 4, there is another operation called folding and unfolding. So this operation is a little bit complicated, and there's a condition for this operation. Suppose that we have a representation G sigma with a pair of vertices such that every odd cycle of G sigma contains either U or V. We call this pair a blocking pair of this signed graph. And if there is a blocking pair UV, then we can resign this signed graph such that our new sign satisfies this condition. So let me explain why. So we have 2 vertices U and V, and every odd cycle contains either U or V. And suppose we delete these 2 vertices and consider the remaining sign. And every cycle contains even number of edges of remaining sign, that means this remaining sign is a cut of the graph. And we keep this cut, and we are back to the original signed graph. So maybe let me draw a graph. So this is our graph G sigma, and there are U and V, and consider G delete UV. So we delete all these edges. And there's a remaining signature, sigma minus delta of U minus delta of V, right? And so C is an arbitrary cycle, and because because every odd cycle in G sigma contains U or V, there is no odd cycle in this graph. So C is even. That means C intersection of, let's call this sigma prime. This is always even, right? That means sigma prime is a cut. So so the sigma should be a cut plus possible edges adjacent to U or V. So so our new signature gamma satisfies this condition. So like this. So we may assume that sigma, for sigma, every edge in sigma is adjacent U or V. Then for unfolding, we split U into U1 and U2 according to the sigma, and we split V into V1 and V2 according to sigma. So every other edge is incident to V1 now, and every other edges, every even edges adjacent to V is now adjacent to V2. Then consider a terminal set U1, U2, V1, V2, and our new graph is H. Then size of T is always 4, and the folding is a reverse operation. Then there is a lemma saying that each cycle of G sigma is a dual of Evencut of HT. So how can you use this operation for generating another representation? So here's how. So we start with G1 sigma with blocking pair, and after we unfold, we have H1 T1, where T1 has 4 vertices, and we can apply some two flips to get a H2 T2, and if we are lucky, we can have size of T2 is 4. Then we fold again to get the G2 sigma 2 with a blocking pair. So they represent the same Evencycle matroid because Evencycle of G1 sigma 1 is the same as Evencut of H1 T1 dual because of the previous lemma. And this is the same as Evencut of H2 T2 dual because H1 T1 and H2 T2 are equivalent. And then we, by the same lemma, we have Evencycle of G2 sigma 2. And we can consider the similar operation. start with the graph, where T1 and T2 has size 4. So we fold, equivalence relation, and unfold. So for the previous one, we call these siblings broken pair siblings, because these two have broken pairs. And for this one, we call this pair T4 siblings, because size of T1 and T2 are 4. So we have 5 operations. So one case is they are G1 and G2 are equivalent, and case 3 and case 3 prime are graphic siblings and co-graphic siblings. And for case 4 and case 4 prime, we have broken pair siblings and T4 siblings. So there are 5 operations, and this is the main result. So suppose that G1 sigma 1 represent the same even cycles. G1 sigma 1 and G2 sigma 2 represent the same even cycle matroid, and G1 T1 and G2 T2 represent the same Evencut matroid. And we assume G1, G2 are 4 connected, and we exclude 5 cases. So G1 and G2 are not equivalent, and they are neither graphic siblings, co-graphic siblings, blocking pair siblings, nor T4 siblings. Then we have only 2 outcomes. So one is there exists G3 such that G1 and G3 are blocking pair siblings, and G2 and G3 are co-graphic siblings. This is one outcome, and the other outcome is very structural. So we call this K6 siblings. So they all look K6, but the arrangement of edge labeling are different. Okay, and we have tried to remove this connectivity condition for years, but the thing is we cannot reduce the connectivity condition into 3 connectivity. And while we are trying to solve this problem, we found the additional cases. Maybe you wonder why this outcome is not symmetric. But for 3 connected, this is our conjecture. If we reduce the connectivity from 4 to 3, the others are the same conditions, same outcomes, but we need one more class. So there is G3 such that G1, G3 are T4 siblings, and G2, G3 are graphic siblings. This is for the isomorphism problem. Any questions? Okay, let me move on to the next problem. So it's a problem about bounding the number of representations. So now we want to bound the number of representations of an even cycle matroid or an Evencut matroid. Unlike the graphic matroid, there are bad examples. For an even cycle matroid, we call this structure donut. So so consider this graph with an arbitrary number of pieces. And these 4 vertices are terminals. So this is our GT, or graph GT, and we can take arbitrary many two flips. So for example, suppose that we pick these two separations and apply two flips. Then now we flip this one, and we flip these two separation, and then it depends on the, oh no, this direction. And consider folding of this, let's call it G prime, T prime, and consider folding with a pair U1, U2 here and V1, V2 here. Then we have some donut-like structure. Right? With the, and the signature and the sign will be here and here. So this folding, and these two are equivalent. And if we fold this one, P3 and so on. So because we picked the two separations arbitrarily, so we can generate exponentially many constructions, and these two are inequivalent. So why we have the bad examples? Because this construction has a blocking pair. So these two are blocking pair of this signed graph, and these two are the blocking pair of this signed graph. And there are many three separations. Three separation of matroid. So each pi union pi plus pj for consecutive indices. So this set always form a three separation of the matroid. We proved that if we excluded these conditions, then we have polynomial number of representations. So this is why we consider this class. So this class called pinch-graphic matroid. So M is pinch-graphic if it has a representation with a blocking pair like this. And we proved that if M is an even cycle matroid that is not pinch graphic, then there are only a constant number of equivalent classes. So what if there are, what if for, what about pinch graphic matroid? So remember there are two conditions. So we have bad examples because G sigma has a blocking pair and there are many three separations. So if we exclude blocking pair, then we have constant number of equivalent classes. And if we exclude many number of three separations, then we have also a result. So if M is an internally four connected matroid that is pinch graphic, that is not graphic, then there is not many three separations, and there are there are only polynomial number of representations, which is big of size of M to the fourth power with a blocking pair. And we have the similar result for Evencut matroid. So for this example, we have many pieces, P1 to Pk. And we identify these vertices, say U, and these vertices, and these vertices, and these vertices. So let's say U, V, X, and W. And our terminal set is these four. And consider these similar pieces. So there are four choices for each pieces. So one is we keep the same direction. Let's draw one more. And the second choice is we can flip left and right. For the third choice, we can flip upside down. So, and the last one is both of them. So for each pieces, we have four choices. So there are exponentially many constructions. And one can check this is actually a folding and equivalence and unfolding. So here we have same terminals. And we call this example shuffle. And similarly, we have some properties. So there are exactly four terminal vertices, and the matroid has many three separations. So we thought this class is also interesting, so we call this class pinch choreographic, and we have similar result. So if M is an Evencut matrix that is not pinch choreographic, then we have constant number of equivalence classes. If M is pinch choreographic, that is not choreographic, and we assume the matrix is internally full connected, so there are not many three separations. Then we can bound the number of representations with 4 terminals by big O of the size of the matrix to the fourth power. This is the end of my talk today. Thank you for listening.
Thank you. Any questions? So what will be the natural next step? Like, do you consider instead of plugging pairs, plugging stickers or quadruplets or something like that? Or
The thing is, we try to solve problems for Evencycle matrix and Evencut matrix, but the thing is, understanding of pinch graphic and pinch choreographic matrix are very important. So if there is no blocking pair or there is no T4 four-terminal representation, then problems are easy. So as you can see here, if the matrix is not pinch graphic or pinch choreographic, there is a constant number of equivalence classes. For isomorphism problem, let's go back to the main result or conjecture. If our matrix G1 sigma, E-cycle of G1 sigma 1 is not pinch graphic and E-cut of G1 T1 is not pinch choreographic, then we have only one result, K6 siblings. So, yes.
What has obstructed you from getting rid of the three connected condition?
So the way we prove this theorem with the full connectivity, we delete one special terminal. So the thing is, for graph GT, and V is in terminal, and GT delete V is G delete V, comma empty set. So if we delete on odd cut, then every terminal set goes away. So then we can use the Street theorem, and because G1 and G2 are full connected, after we delete one vertex, the graph is three connected, and there is no two flips or one flip, so it makes the problem easier. But if we keep the three connectivity, then maybe we have some two separations, and we need to care about that, and that makes us some other constructions, and that gives the third option here.
we have a question from the live chat. So for sufficiently high connectivity, do you conjecture that there will only be a constant number of inequivalent references?
That's a very nice question. I don't know. Let me think again. I think it is true. So for my master's thesis, I tried to prove the following. If we excluded donut structure, then we have a polynomial number of representations classes. So if our matrix is highly connected, then there is no this structure. So that means there are we need to define another class. So for this operation, so we call this flower class, and the bound but the bound is very bad. It was like size of n to the 14 or something, and it is very far from the type, and the proof is hideous. So we try to find another way. So we exclude the blocking pair first, and then we consider the connectivity.
Any complexity, algorithm of complexity known for, like recognizing intersect matrix or finding representations for given oracle given intersect matrix. Like for instance, sometimes there are theorems that you need exponentially many correlates to decide whether something is.
You mean if the matrix is given with the oracle?
Yeah, define oracle.
For Evencycle matrix, I don't think there's a polynomial time algorithm, because Professor Jim Gillam mentioned about this, and he said that we can relax one circuit of the binary matrix, and there's no way to recognize all the relaxations, because there are exponentially many relaxations. So there's no way to recognize Evencycle matrix in polynomial time.
Yeah, but is that so you start with the uniform matrix and then you relax one. I mean, you need to know that one is Evencycle matrix, the other one is not Evencycle matrix.
Yes, and there are exponentially many relaxations. So, but we constructed the polynomial time recognition algorithm when the given matrix is given by binary representation. And that algorithm depends on the previous taught algorithm to recognize graphic matrix.
Any other